So welcome back to Finite Element Methods, Math 574. This is class number 8. Last time we introduced some discussion about the finite element method in one space dimension. We talked about hat functions. These were the basis functions for our piecewise linear finite element spaces. And today we're going to continue in 1D talking about quadratic finite elements in 1D, and then we're going to go into a discussion of finite elements and finite element method in 2D, and I'll show you how you construct approximations and finite element approximations more specifically in that setting. So last time when we were talking about 1D finite elements, we were talking about these things called hat functions. We were talking about them subject to some partition or some grid that you had put down over the domain. And we're looking at this very particular model domain, omega equals the open interval 0 to 1. So all of our points are in the closed interval 0 to 1, okay, for our partition. Remember, we had this thing called the partition spacing, and by definition, the partition spacing was equal to, let's see, how does it work? It's xi minus 1, right? By definition. Now, under the assumption that each one of those points in our partition is equidistant from the others, well, from for the nearest nearest neighbors, then we can well, that's equivalent to this assumption that hi is equal to some common mesh spacing h for all I between 1 and n plus 1. So in this case, if I put the basis functions phi j and phi I into my bilinear form, which is just, remember what my bilinear form was. So this a was equal to the integral from 0 to 1 of phi j phi I prime, both cases, dx, right? And so if I put those two things in there, I can calculate the weak derivatives because these hat functions have well-defined weak derivatives. So so this is how I define the ij entry of my matrix, my so-called stiffness matrix, so aij. And in this case, where all the mesh spacing is uniform, then my little formula that we gave last time simplify. And so I get this tri-diagonal matrix emerging, where I have 2 over h on the diagonal minus 1 over h on the super and subdiagonals, and zeros everywhere else. So this is the matrix that I get whenever I have that very simple case where, with a simplifying case where all of the mesh points are equidistant from their nearest neighbors, some spacing h. Just by construction, the matrix A has to be a symmetric matrix, but in this case, it's a very simple formed symmetric matrix. It's just a tri-diagonal symmetric matrix. The super and subdiagonals are exactly the same. They're just they have these common entry of minus 1 over h. So if you're familiar with the finite difference method, a very similar matrix comes out in that methodology. So I encourage you to go back into your numerical analysis course notes or your textbook and look at the stiffness matrix in the case where your approximation is given by the finite difference method. You will see that the stiffness matrix that emerges from that case is remarkably similar to this one. The only difference is it's off by a factor of 1 over h. Now, you might remember from our discussion of the general Galerkin method that once we have a basis for our finite dimensional space, we can transfer or we can reformulate the approximation problem as a matrix vector problem. Remember, it was A times U equals F, where A was the stiffness matrix, U was the displacement vector, which represents the approximate solution in some sense, and F on the right-hand side was this thing called the forcing vector. So this forcing vector, remember, was calculated according to a formula for I between 1 and m, Fi, that is, have a slight error here, slight typo. So this should just be, so my notation is usually this. If I want to extract the ith coordinate of a vector, then we usually give that the name of the vector. Okay, so that using the same symbol, but we just put a subscript I. Okay, so this means extract the ith coordinate from the vector inside the box. Okay, so by definition, we said that that ith coordinate was equal to the integral of f against phi I, the ith basis function. So this is just the L2 inner product, or the integral. And the integration limits are 0 and 1. We're going to integrate this, of course. Now, this function here is just going to be a hat function, so it does its usual thing, right? We don't need the derivative of the hat function there. So what you're integrating against is, for each I, you're integrating f, which, let me see if we can draw the picture here. So we've got this function f, which is sort of doing its thing, and then we have an interval. Here's our xi. So our ith basis function looks like this. So well, it doesn't necessarily look exactly like that, because this is suggesting that they have the same value. They don't necessarily have the same value at xi. So here's my function f, and here's my ith basis vector phi I, and what I'm doing is I'm computing the integral of the product of those two things. Now, the product of these two things is not necessarily a simple function. It could be quite complicated. By our assumptions, f is an L2 function, so L2 functions don't even have well-defined point values in particular. So it could be a rather complicated function whenever I make this product. And so I don't know what is going to be the result of doing this calculation. All I know is that it can be easily broken into two subintegrals, one over this interval and one over this interval. And that's because phi I has this definition, this tripartite definition, right? So we say it's 0 except on ki and ki plus 1, where it has some sort of linear transitional value. So here's the integral over ki, and here's the integral over ki plus 1. Okay, kind of nestled in there. So what are these integrals? Well, I don't know, because f could be a fairly complicated function. But let me give you some sort of indication what it looks like in terms of values. So let's suppose that, and by the way, another way of writing it for a uniform mesh is like that. So all I've done in that is just taken the assumption for face value that hi and hi plus 1 are both equal to this common value of h. So I can pull that common factor out. Now, let's suppose that f is a special kind of L2 function. It's constant on each triangle ki. So it's equal to the sum of characteristic functions. So characteristic function chi, that is just a characteristic function that turns on in the interval ki. Remember, the interval ki is an open interval. So anyway, it turns on and it goes up to 1, right? And so what I'm doing is I'm making a linear combination of those functions that turn on those open intervals, ki, and I'm multiplying that times a constant. Okay, each one gets a different constant, and I'm going to call those constants fi tilde. All right, so I hope that you can see that this is just a piecewise constant function. Now, everywhere this is not turned on, I'm just going to, then f is just going to be 0 at those points because nothing's happening there. And so what does this function look like? So it's going to be some value here to there, maybe another value here to there. And now I didn't say what's happening. Let's put another one in here. I didn't say what is happening at these points. Okay, so that means they're forced to just be 0. It's just forced to be 0 at those points. But notice that that really doesn't matter at all because, in fact, well, it's 0 everywhere outside of there. That doesn't matter at all because all that matters is, that those points there with respect to my integration are just going to be points on a set of measure or in a set of measure 0. So they're not going to change the value of the integrals. Okay. Now I'm going to plug in these values. I'm going to plug in this function for f. And now what happens is when I plug that in, it's a very simple calculation to see this. Then I'm just going to pick out those constants on the particular interval. So this is the ki interval, and this is the ki plus 1 interval. So I just get those two constants coming out. Well, then I can integrate this. I can pull this constant out, pull that constant out. I can integrate this very simple equation here. It's a linear equation. It's basically the area of a triangle, and it's we don't even need to know calculus to do that one because it's the base, 1/2 the base times the height. The height is going to be h over, well, it's h, and then we have another h coming from the thickness of the interval. And then, of course, we're going to divide by 2 because it's the area of a triangle. So this works out after the cancellation of all the h's that we need to cancel. It just works out to be h over 2 times the value of f on the ith interval. Let's say that one, or sorry, that value there, and then the value on I plus 1. Okay, so this kind of gives you an order of magnitude of what this function looks like for a very simple case where f is a piecewise constant function. Otherwise, you just got to do the integral. There's no kind of way around it. You've got to know how to integrate that function. That's kind of the Achilles, one of the Achilles heels of the finite element method. This is based on integration. So to compute my stiffness or my forcing vector, I have to do an integration. And so sometimes you can't do this exactly and you've got to approximate. But approximation is kind of what we know how to do as numerical analysts. Now, recall that the Galerkin method or the Galerkin approximation told us how to find the approximation that we're interested in. So we're interested in finding the approximation UH from the piecewise linear finite element space. And remember, going back to the last lecture, this was the finite element space where on each interval the function was linear. You all know what a linear function is, or a polynomial of degree 1, I should say. And it's globally continuous, and it has 0 boundary conditions. So that's going to be my universal notation to indicate that the boundary conditions are assumed to be 0. So I look for my solution in this space, right? And we showed that the Galerkin approximation, or at least alluded to the fact, is equivalent to this. Now, this is not a generic test function. This is the test function phi I. But it's not hard to show that if I put in a generic test function and then I write that test function in terms of its basis expansion, and these are the basis functions from B0I, 0, 1, then I can show that my generic Galerkin approximation is just that. In other words, I can use the m basis functions from the basis expansion of, or from the basis, this is the finite element basis for this piecewise linear polynomial space. This is just the approximation that I get. Now, I can do the same thing. I can assume that, first of all, it's not hard to show that the solution exists and is unique, as we've already done. Now I'm going to write UH in the same basis expansion, or in the same basis. So it has a unique basis expansion, and the coefficients in the basis expansion I'm going to call UI. Now this is all in the way of a review because we've done this before, but in the generic setting. So I'm looking for this U vector, which has as its components the entries or the coefficients of the unique basis expansion for my approximation, my Galerkin approximation UH. I've already told you how to compute the stiffness matrix entries. I've told you how to compute the forcing vector entries. And so now all I have to do is solve this symmetric positive definite matrix problem, and I get U from it. And then once I have U, that's a vector, of course, in Rm. It's not the finite element solution. It's just the coordinates of its basis representation. So if I want the finite element function, I'm going to put these coordinates in this expansion, and then finally I can plot that out as some sort of piecewise linear function. So U is what we call the displacement vector. So we showed previously that A is not just symmetric. By the way, it's clear that it's symmetric and it has positive diagonal elements. So you could postulate that this is symmetric positive definite, but we actually already proved that, and we did it in such a way as it doesn't require, so all that is required in that case is just knowing a certain small fact. So you can go back to the notes to find that. In fact, what fact is it? It's the coercivity of the A bilinear form that shows that you have the symmetric positive definiteness. I'm not going to redo that here. So we know that this equation can always be solved. So U can always be found, and the approximation always exists and can be constructed. Now, the other thing, the important point about the finite element method is not that the stiffness matrix is symmetric positive definite alone. It's that the stiffness matrix is symmetric positive definite, but also quite sparse. That is, most of the entries in the matrix A are zeros. And this is a trait and a very important quality of the finite element method. That is that for at least the model problem, A is symmetric positive definite, but even more importantly, A is sparse. Okay, it's a sparse matrix. It's got mostly zeros in there. So one thing this tells you is that when you're coding, you want to take advantage of the fact that there are lots and lots of zeros in your representation of the stiffness matrix. You don't want to actually ever write out a zero, which you know is going to be a zero. It's a little bit like saying, well, if I have a matrix A and I know that it's mostly zeros, but I wanted to find the matrix vector product of A times U, then it doesn't pay in MATLAB, for example, to represent all those zeros, because all those zeros are simply going to go away when I do this matrix vector product. So you want to take advantage somehow of the sparsity of A, and we'll talk more about that later when we talk about implementation issues. So that's the piecewise linear case. Let's review the piecewise quadratic case in 1D. It starts off more or less the same. We have this very simple domain, this open bounded domain omega. And what we're going to do is lay down a partition on that domain omega. And a partition that follows the rules that we defined earlier. It means x0, the beginning point in the partition, has to equal 0, the right hand or the left hand endpoint, and xm plus 1, the largest value, or say the value in the partition with the largest index, has to equal 1. And then, of course, the partition has the rule that x1 is greater than x0 and x2 is greater than x1. And in general, xi is greater than xi minus 1, etc. What we're going to do here for quadratic elements is whatever partition you lay down, we're going to go back and look at the partition endpoints, and we're going to calculate the midpoint from that. Very simple calculation. So how do I get the midpoint of, say, the interval ki? I just take xi plus xi, well, I can do it in a couple of different ways, xi plus xi minus 1, and that gives me the midpoint, and I'm going to label that midpoint xi minus a half. The generic one here is picked so that this super, or the subscript, looks like it's an increasing value. So I have I here going to the right, I'm going to have I plus a half, and then going to the right further, I have I plus 1, and this pattern repeats. So that means that I use this definition. So that is for this guy here, generically, you just take xi plus 1 and xi and average them. And we're going to do this for I between 0 and capital M, right? So that's going to give me, the first point is going to be x 1/2. The second point is going to be x sub 3 halves and x sub 5 halves, etc. How many of those are there going to be? Well, there's going to be precisely m plus 1 of those. Okay, so there's the first one, and there's the last one in my collection of midpoints. Now, these are perfectly in the center of their respective quote-unquote triangles or intervals. So this guy's right in the dead center of ki. And this guy here is right in the dead center of ki plus 1. Okay, so that's the full ki plus 1 interval. As before, hi is defined as xi minus 1. This calculation is valid for I between 1 and m plus 1. And I'm going to call these triangles because in 2D they really are triangles. The triangles are the intervals. Ki are the intervals xi minus 1 to xi, open intervals, that is not including the endpoints, and those are also indexed from I between 1 and m plus 1. All right, so we're just getting all the notation in order. Now, the nodal set that we're going to use for the quadratic finite elements is different than that for the piecewise linear finite element set. And that's kind of probably obvious to you already because, well, we didn't define these midpoints, or we didn't worry about what they were when we were defining the piecewise linear finite element spaces. So these midpoints must be of importance for constructing the quadratic finite elements, and they are. So the quadratic nodal set is the set of nodes, okay, that includes all of the nodes from the original partition, and it includes also the midpoints. So in other words, it's the partition points union with all the midpoints that I just calculated. Does everyone see that? So it's sometimes these are called the vertices, and these are called the midpoints. And the collection of all of them are what we call the quadratic nodal set. So n for node and 2 for quadratic. And it's just the union of the partition and the midpoints of the partition. Now, we also need a nodal set to cover the case whenever we have the homogeneous Dirichlet boundary conditions. And what we do with homogeneous Dirichlet boundary conditions is we remove the degrees of freedom at the two endpoints because we're going to force the function to be 0 at those endpoints. So what I do when I get the homogeneous quadratic nodal set is I'm simply going to take the previous set and I'm going to drop the two endpoints associated to it. Well, that just means that in this partition, I'm going to drop the 0 and the n plus 1 points. And so this, instead of having this set in my definition of the nodal set, I'm going to decrease it a little bit, dropping the endpoints, and then that means my index runs from 1 to m only. So this latter set is exactly the same as this one, except that it doesn't contain the two endpoints, okay? So we could have defined it simply by, we could have said this is equal to this, and then set minus out the two endpoints. That's another equivalent way of doing it. So what do I mean by that? I mean that we could have said, let me give myself a little bit of room to work. So this is just equal to the original nodal set and 2 set minus x0 xn plus 1. Same thing. And in any case, this set does not contain, I should say instead of this latter set, the set does not contain the endpoints. That's all we're doing. We're just rejecting those. And the reason is because those are not going to be degrees of freedom for the case where we have the homogeneous Dirichlet boundary conditions. Now, what I would really like to do is instead of having these written as two different sets of points, I'm going to call them all, I'm going to bring them all into one unified collection of points. How can I do that? Well, I'm just going to say whatever is in that nodal set N2, for example, let's just agree that we could write those as a set of points zi from I equals 0 to n plus 1, such that the order of these nodes are strictly increasing. So in other words, this becomes a partition itself, okay? But it's a partition that contains the original partition and the set of midpoints. But I'm just going to give those a different moniker. I'm just going to call those Z0. And I'll show you how these line up with the original partition points and the midpoints in a moment. All I really care about is writing this as if it were a partition or the partition that I wanted to begin with. It's not exactly the same as the partition that we started with. Now, it's not hard to show that the number of points in this set is equal to, or let's say it's naturally indexed from I equals 0 up to n plus 1, where n is equal to 2m plus 1. I'm going to show you that that's the correct number in just a second. Now, how can I get the homogeneous quadratic nodal set? I just drop this point and that point, and the reason I'm going to drop them is because they're not going to be degrees of freedom in my problem. So here's an example. Here's an example where m is equal to 3, and according to my formula, n has to be equal to 7. Okay, so that's not exactly the number of points in this nodal set because I count from I equals 0 to n plus 1. But that means that the number of points in this set is going to be capital N plus 2. All right, so what does it mean whenever I choose m equal to 3? Well, the original partition is of size, it's kind of like size 3. It's not really of size 3. It actually has 5 points in it, namely x0, x1, x2, x3, and x4. I just call it 3 because when I eliminate these 2 points, then there's going to be 3 left, and that's a nice number to work with. So there's 5 points in that original partition, 0, 1, 2, 3, and 4. So it's off by 3 by adding these 2. So that number becomes 5, right? So how many points are going to be in my N2 set and how many points are going to be my N02? Well, to figure that out, let's first collect all our points as instead of, we call these vertex points, and then we call these guys here edge midpoints or just midpoints. Okay, so when I create this larger set N2, I'm combining these together. I'm unioning them together. So I'm going to call those z points, and the z points are what I call nodal points. They're always called nodes. Okay, so nodes, I'm going to differentiate in my finite element language again and again. Those are always vertices of triangles plus midpoints of edges, and maybe some other points in there as well. But the nodes are where things are happening. Okay, so the partition itself just has vertices, but my nodes have more points in them. All right, so how many points are going to be in this nodal set? Well, N2 I'm claiming is going to have 9. That should conform to my understanding because I said if I start with m equals 3, then capital N is equal to 7. So the number of points here is going to be capital N plus 2. That should be 9. And let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. And what about the number of points in N02? So those are the interior nodes. So there's exactly 7 of those, and that's exactly equal to the number n. So the way I've made things work is that n is the number of points in my interior nodal set. Okay, the set of interior nodes. So that guy. If you do a couple more examples like this, you can see how the numbering convention works and how it all works out. Now, usually for our model problem, we're going to set the degree of freedom for our approximation function 0 at these 2 points. And that's precisely why we get rid of them in this nodal set, as I'll explain in a moment. Now, and by the way, this distinction is a little bit tricky, so you might need to get used to it by doing a few examples on your own and also kind of living with this definition for a little while. It's tricky. Well, now we want to build basis functions for our piecewise quadratic finite element space. Let's do the space, the normal space first, and then we'll do the space without degrees of freedom at the endpoints second. So let phi I be in the space of piecewise quadratic finite elements defined via the following rule. It's a very simple rule. We're just going to say phi I evaluated at the nodal point zj is equal to the Kronecker delta symbol delta ij. So that means if I and j are equal, then this is just going to be 1. And if they're not equal, then this function value of the Kronecker delta symbol is just 0. So it's just saying phi I has its is basically turned on at the ith nodal point, and it's 0 at all other nodal points. That doesn't mean it's identically 0 everywhere except for the ith nodal point. It doesn't. And I'll show you what these functions look like momentarily. So this requires my understanding that my nodal point is written like this, and these, of course, are my nodal points written in order z0 up to zn plus 1, okay? This is the so-called quadratic nodal set, okay? Maybe we'll write it here just to emphasize. So 0 is equal to z0, which is less than z1, which is less than zm plus 1, which is equal to 1, right? So it has this increasing order. All right. So now I'm going to make a claim that you should be able to prove in a homework exercise, but I'm going to try to argue why it's true and give you a kind of proof by picture. Okay. So the functions phi I that are defined above are uniquely defined by this 8.1 condition. by telling you that the function is in M2 and it has to satisfy that it's that phi I at zj is the Kronecker delta symbol, delta ij. That completely and uniquely defines what that function looks like as a function. All right, so this is a complete definition. It's not, doesn't allow any ambiguity. Furthermore, we have two sets that I want to consider coming from these. The first one, I'm going to take those phi functions and I'm going to count I equals 0 up to n plus 1. Remember I said n is equal to 2m plus 1. So 2m plus 1, that's going to give me 2m plus 2 for my total number of, well, that's going to be not the total number, but it's going to be the largest index for this this set in terms of m. So basically, I'm counting all of the phi I functions that I just defined over all of the nodal points. Now, for the case where I don't have, for my model problem where I have 0 boundary conditions, I'm going to eliminate the degrees of freedom at the two endpoints. And the way I do that is simply don't count the basis function associated to I equals 0 or the one associated to n plus 1, and I stop at I and n. And again, n was 2m plus 1 by definition. So these, I claim, are bases for the respective spaces M2, which is a vector subspace of a finite dimensional vector subspace, it turns out, of H1, and M02, which is a finite dimensional vector subspace of H01, respectively. So if these are really bases, then that tells us what are the dimensions of these spaces, right? So the dimensions of these spaces are precisely equal to 2m plus 3 in terms of the number m for this guy, and 2m plus 1 in terms of this dimension. So this number here is also just equal to, that's just n. Let's see. I guess I can symmetrize that by saying what this guy is as well. Right, so we said 2, so this is going to be n plus 2, right? Yeah, n plus 2. There we go. All right, that's by design. Now, let me show you how to prove this. Right, so what do I have to do to show that something's a basis? I have to show that the basis functions span the space and they are linearly independent, okay? So I have to first say, well, if you have a generic function from the space, can it be written as a linear combination in the basis? So I claim that this can be done. And then the second thing is I have to show that the basis elements are all linearly independent. So the easiest way to do this is just make a linear combination and set it equal to 0, and so that show that the only way that that can be satisfied is through the trivial expansion. So I'll leave those to you. I want to answer the question, the kind of primordial question, and that is, why does the definition that I gave above completely and utterly define these basis functions and then and uniquely define them? And then what do they look like after doing that? Well, let's think about this. What does this definition mean? It means that it all know, according to the, well, first consider phi I and evaluate it at all the different nodes. The only one which should be non-zero is whenever I and j equal to each other. So let's go down here and look at this. Suppose that the node that I'm interested, so this is my line here, and of course out here somewhere is 0 and out here is 1, and so this is just a snapshot of what's going on and kind of in the middle of the mesh. So I'm interested in this point right here, zi. So let's look at that. I'm looking for a function which is equal to 1 at that point, zi, and it's equal to 0 at all the others. So first of all, notice that this function phi I satisfies that condition. It's 0 here, 0 here, and 0 here. And what else do I know about this? Well, this guy is a quadratic function, as I'll show you in a moment. So it's a quadratic function that is 0 here, 0 here, and exactly 1 there. So on that branch, that's how it's defined. What about over here? Over here, that quadratic function is 1 there, it's 0 here, and 0 there. And everywhere else, it's equal to 0. So let's first agree that this function phi I looks like it satisfies what I'm asking for, right? We're saying that it's equal to 0 at all the nodes except for the ith node, and there it's equal to 1. I should probably say here that this value is equal to 1. Okay, so does everyone agree? Right. That looks like that looks like a function that satisfies that condition. The question is it a unique, does it uniquely define how that works? You know, is that the only function that has this definition? Well, let's think about it. So if I want a function to be equal to 1, so I'm going to give you some hand wavy arguments about this. Um, at this node here, is there any other way I can do it so that it's going to be a piece? Remember, it has to be piecewise quadratic, and it has to be globally continuous, and it has to satisfy the conditions that I've set, right? I said phi I has to be piecewise quadratic, it has to be globally continuous, okay? And it has to be 1 at this node and 0 at all other nodes. So I guarantee, or I don't want to say it like that. I'm suggesting that that's the only way you can do this. Okay? I'm not, I won't give you all of the explanation of why. I hope it becomes clear once you start thinking about it and writing it down. That this is the only way I can satisfy that condition. It has to be piecewise quadratic, globally continuous, and it has to have the value 1 at its particular node of definition or node of interest, zi, and it has to be 0 at all other nodes. Now, that answers the question, at least if you believe my very hand wavy argument. That's how I construct that one basis function. Now, you could, how could you prove that that's the unique definition? Suppose there's another way of doing it. So another way of doing it would have to have the same qualities, but what I could do is show that that other one must be exactly the same as this one. But notice that the shape of this function is kind of just, you know, it's this funny shape here. That's what the full basis function looks like. I can make the same argument for the basis function, which is 1 at this node, okay, phi I plus 2. It has to satisfy the same thing. So ultimately, I can make this argument at one node. I don't have to make it at every node because all these basis functions have the same structure. That is, if the basis function is at a node, or is supposed to be 1 at a node here, which was a vertex node. Okay, so these are vertex nodes here. So vertex node, that means it's in the original partition. In the original partition P. What about what do the basis functions look like for the midpoint nodes? So these guys here, these odd ones, well, they're not, I don't really know if these are odd or not, but so these guys here are midpoint nodes. What do the basis functions look like there? Well, it's got to satisfy, it's got to be 1 at this node, which is a midpoint node now. It's got to be 0 at that at those two nodes, those two nearest neighbor nodes, and then it has to be 0 everywhere else. So that's what that basis function looks like. And again, I argue that guy definitely satisfies the criterion because this is going to be a quadratic function. It's just an upside down parabola. What about for this guy? Same argument. It's got to be 1 at the midpoint node. It's got to be 0 at these two neighboring endpoint node, or these two neighboring vertex nodes, and it's going to be 0 everywhere else. So again, the argument that that function works doesn't have to be renewed at every midpoint. You can use the same one. So these functions here are what we call bubble functions, okay, because they are entirely supported over this triangle Ki, okay, the ith triangle. So now it's sometimes a good idea, at least in 1D, to think about these functions and constructing them kind of separately. I've already given the construction in a kind of separated way because my construction for the vertex nodes is different from the midpoint nodes. Okay, but it's still, each one of these functions satisfy my very simple criterion that they're functions in M2 and satisfy this very simple phi I evaluated at zj is equal to delta ij, that criterion there. So all of these functions satisfy that. But it's often easier to break these into two separate function categories. For vertex nodes, so these are going to be the basis functions at the vertex nodes. And these guys here are the basis functions that we called bubble functions earlier. So this is at, these guys are the bubble functions at the midpoints. And these here are at the vertices. Now, this little formula works out perfectly. These are two quadratics, which I'm going to join together over the two neighboring intervals ki and ki plus 1. So what does this look like? And by the way, it's 0 everywhere else. So basically, it makes sense according to the picture that we had previously. We've got this point. Now we're going back to the original partition that we had. So there's our xi minus 1, xi plus 1. So this is triangle ki, and this is triangle ki plus 1, right? So we're going to put in the midpoint through its original numbering. Okay, there's the midpoint, and there's the midpoint for that interval. But notice what these two quadratics are saying. It's very simple, right? This quadratic, this guy here, has to be 0 at xi minus 1 and xi minus a half, the midpoint. So this guy here, I'm claiming, this first one, is precisely constructed so that its shape is like that. And it's going to take the value 1 at this point, xi. How do I show that it's going to take the value 1 at xi? Just put that in for the value of x. You get 1 coming out. What about this guy here? Well, this guy has to be equal to 0 at the point xi plus 1 and xi plus 1/2. That's the midpoint there. Let me scoot these down a little bit. Or maybe I'll move everything up first. Give myself some room to work. So this part over here according to that line, is engineered so that it looks like this. See if I can draw a good version of that. Okay, and then it's 0 everywhere else. That's exactly what this function is doing. This definition is doing. With the caveat that if I is equal to 0, then I really didn't define the triangle K0. So I'm just going to assume that K0 is equal to the empty set. And if I is equal to m plus 1, then this set here doesn't exist. So just take that to be the empty set as well. And so that definition wouldn't come into practice. I'll show you what this looks like in a minute. Okay, now what about the bubble functions? Remember, the bubble functions are just these kinds of functions. All right, so I claim that, well, let's go back to our little picture here. The bubble function should be, let's draw those in blue maybe. It's going to be with respect to, we're defining it on this interval ki generically. So it should be 0 at xi. And it should also be 0 at xi minus 1. Right? So the bubble function that we're defining down there is like that. Okay, so that tells me this thing here I'm calling psi I plus half. And the red thing I'm calling my new function, new I. Okay, so those are the two definitions I've just given there. Now, these definitions have to be modified if xi is a boundary node. So whenever I is equal to 0 or m plus 1. And I've told you how to do that here. So all of these functions here, which were defined by this very simple rule, can be broken down into two classes of function. One are these functions which turn on at these the original partition points, or what I call vertex points, and then these bubble functions which turn on at the midpoint. Okay, so at the midpoint there's 0. So this whole family here contains both of those, right? It's kind of like the union of the two sets, these vertex functions and these bubble functions. And you can find the correspondence is kind of straightforward. Vi, or I guess it's new I is equal to phi 2 times I, from I equals 0 up to m plus 1. And you need to check this. And psi I plus a half is equal to phi 2i plus 1 from I equals 0 up to m. And so you'll see that there's exactly the right number of basis elements in these sets. Okay, so again, how did I define this in such a way that now you put them into two different collections? One is for whenever we don't have degrees of freedom at the endpoint, and one where we do. So you may have to sit and think about this definition a little bit. Hopefully the problem set will also, the new homework set will also help you think about these things. Draw them out, put them in their proper places, do some manipulations with them, etc. So we've given not a complete discussion of what's going on with the finite element method in 1D, but we've given enough of a discussion for now that I want to kind of leave that to the side and now go into what the finite element method looks like in 2D. We're not going to be completely general about our discussion, but we're going to be fairly general. We're looking mostly at the case of the model problem on a very specific type of domain. The domain that you can have in the back of your mind is a square. That's fine. For the future, however, solving problems where the domain is maybe has a curved boundary like a circle, that requires a bit more sophistication that we're not going to talk about for at least a while, and may not talk about at all in this course. But I can point you in the right direction if you have some interest about that as a subject. For now, we're going to think about very simple, open, bounded set, we're going to think about what are called polygonal domains. So polygonal domain just means that all the boundary of this set are just straight lines. That's it. Okay, so polygonal just means the boundary is comprised of straight lines. The fact that it's open means that we're not actually going to consider points that are on the boundary to be in the set. And then the other part is we want to look at only bounded polygonal domains. So again, a polygonal domain is a set that is just comprised of a bunch of straight lines, or whose boundary is, I should say. So something like that, okay? So there's a perfectly good omega for our purposes. Um, Now, we're going to consider what we call a triangulation of that domain. So what does it mean to triangulate the domain? Triangulation means that what this is going to be a set of sets or a collection of sets. Okay, the triangulation is a collection of sets. Each K is going to be a triangle, but we'll get to that in a minute. If I take the union over all the sets in that collection, then, or sorry, if I take the union of those sets, the closure of those sets of all the sets in the triangulation, then I need to get omega bar back in the end. So I need to get the closure of my original set omega. So I take the collection that I have, I close each set in that collection, and then I take the union over all of the triangles or the elements in that collection, and that should give me the closure of the original set. So that's one point that a triangulation has to satisfy. The second one is that, not sure why. Had some letters disappear in my word. So this should have said each K, that's not, yeah, okay. Yeah, each element of the triangulation has to be a subset of the open set, and it has to be an open, non-degenerate triangle. Okay, so each element in that collection has to be a subset of omega. It could be all of omega, by the way. If I start off with omega being a triangle, then that's fine. But each K has to be an open, non-degenerate triangle. What does non-degenerate mean? It means so a degenerating triangle is one where you basically have no area in the middle. So if I push down on this vertex and squash it so that there's no area in that triangle, that's called a degenerate triangle. So I want all my triangles to have some positive area in the middle, okay, in the interior. Non-degenerate triangle. And then lastly, I think that's the last one. Yeah, third one. For any two distinct triangles, Ki and Kj in the collection that are disjoint, don't need that. I should say such that for any distinct triangles, oh no, this is actually, should have studied this more carefully, what I just wrote. For any two distinct triangles in the triangulation, they need to be disjoint, okay? They need to be absolutely disjoint from each other. But if I take their closure, if I look at the intersection of their closure, then there's three choices. Okay, so if I remember, each triangle is an open set. So if I take the intersection of two, they have to be disjoint. But if I take the closure, then I'm going to have three possible choices. Either one, they are the intersection is empty, or two, the intersection is a common vertex, just one point, or 3, the intersection is a common full edge of the triangle KI and KJ. So here's some examples. So remember these 3. I kind of botched them, but I hope I recovered enough so that you understand it. If I take the union of the collection of triangles, or at least their closure, then I have to get the closure of the original set omega. Each element of the collection has to be an open, non-degenerate triangle that's a proper, well, not necessarily proper, but is a true subset of omega. And lastly, each intersection of those of any two distinct triangles has to be empty, and when I take the intersection of their closures, I can only have one of these 3 choices. Okay, so let's take 2 triangles. So first of all, let's take this guy and that guy, neighbor, right? The triangles are only the interiors of those triangles, okay? The sets K, I, and J. So what if I take the intersection of the 2? Well, they don't see each other, and those 2 triangles are disjoint, right? What about this guy and that guy? Yeah, again, disjoint. I can take any 2 triangles in the collection, and I take their union or take their intersection, and I get the empty set, so they're disjoint. What if I take the closure of 2 triangles? Okay, if I take the closure of this triangle and that triangle, then they contain the boundary. Take their intersection, I'm going to get a full edge. What about these 2? I take their intersection of their closures, and I get a point. That's called a common vertex, right? So that's this case. So it looks like this mesh satisfies all 3 requirements or this triangulation satisfies all 3 requirements and therefore is a proper triangulation. But what about this guy here, over here? This is comprised of triangles. Each triangle is an open triangle and a subset of omega. But the problem is, let's take, for example, this triangle and that triangle. Take their closures and take the intersection. Well, the intersection is going to be a full edge of this triangle, but only going to be a partial edge of that triangle, right? So there's the intersection. And likewise, if I look at this triangle and this triangle, take their closures, take their intersections, I get an edge which is not a full edge. That's the problem with this triangulation. It has what are called hanging nodes. Hanging node is whenever I have a node in the middle of another edge of a triangle which isn't completed. Okay, so giving a full definition of what a hanging node means is hard, but the picture is a lot easier. You know what it is when you see it. This triangulation over here does not have any hanging nodes and therefore is a complete triangulation, true one. Okay, so that's what we mean by a triangulation. The next thing we need to know is how to compute a mesh spacing for the mesh. So this is sometimes called TH or tau H, be a triangulation. So this is kind of a funny notation. It's a kind of shorthand. This thing on the right-hand side just means a set of triangles, a set of sets. Okay, the elements of that set are open triangles, and they can be indexed, of course, but I'm not giving them any kind of index here. And the reason is it's not clear what indexing you should choose. Should I count like 1, 2, 3, 4, 5, 6? Or should I count them in clockwise order, swirl into the middle? The ordering of the counting is kind of tricky. So just as a shorthand, we don't give them any kind of indexing. We just say, well, it is what it is. So let tau H be a triangulation of the polygonal domain omega. So we're going to define the mesh spacing HK of each triangle to be the maximum of the distance between any 2 points in that triangle. Okay, so what does that mean? Well, I have a picture here. So if I take any 2 points in the triangle, and I calculate the distance, that gives me a number. If I take the maximum, then for this triangle, it looks like the 2 points which are separated by the most distance are the points at these 2 vertices. Okay, and so that gives me my HK, right? HK is the max taken over all possible distance of any 2 points drawn from the same triangle. And I'm drawing it from the closure of the triangle. That allows me to put those 2 points at the at the uh, at the vertices, which instead of having to use a supremum instead of max. Now the number rho k. Oh, I missed one here. So h is then defined as the maximum of all the h's. Okay, all the hk's taken over all k's in the triangle. So this is similar to our definition for h in the one-dimensional case. It's just in the one-dimensional case, we have a nice indexing that's not available in 2 dimensions. The number rho k is the diameter of the largest inscribed circle in K closure. So in this case, it looks like the largest ball or the largest circle that I can put inside of this triangle is this one. And so rho k is going to be the diameter of that largest inscribed circle. Now, why am I interested in those 2 numbers? Well, I'll get to that a little bit later. All we need to know now is that HK is always going to be bigger than rho k. And so this ratio, HK over rho k, which is bigger than 1, is what's called the chunkiness parameter. And it's going to be important for our analysis later on in the course. Is there anything else I want to say about it? Well, so one thing is the chunkiness parameter as a ratio can degenerate or can become very large. How is that possible? Well, let's look at an example. So suppose I have a triangle like this. So this chunkiness parameter is very large. Why? Because the HK for this triangle is pretty big, but the interior inscribed circle, rho k, is pretty small, right? It's so small that I can barely fit the rho k in there, but you get the idea. Okay, so rho k looks like it's going to be actually just the distance between those 2 lines. So this ratio in this case is going to be fairly large, right? Well, it turns out triangles like this with a large chunkiness parameter are not good. We want a chunkiness parameter which is as close to 1 as we could possibly get it. And the ones which are close to 1 are close to being equilateral triangles. And so those turn out to give us mesh with a very nice quality. Whereas meshes with a large chunkiness parameter turn out to be kind of not so useful for us. Or not that they're not useful, it's just that it turns out that that can be in some ways bad for our approximation methods. Okay, so it looks like we're not going to get much further in our definition, so we'll pick up there next time. What we're going to try to do is I'm going to try to show you what is the analog of the things that we need to define piecewise quadratic versus piecewise linear functions on these spaces. And then I'll try to exhibit what they look like, and then we'll collect them all together and talk about their properties. But we have to end the discussion at that point for now. So we're talking about 2D finite elements, and we're going to pick up somewhere right in here next time. All right, so with that, I'll end the class and I'll take your questions.